All right, so welcome everybody. It feels a bit, like 2019 all over again that we have a conference in real life. It's not as easy as it used to be, but thank you everyone for joining. It's great to see so many people. Few announcements, I will be short. If you take coffee, please take it upstairs on the terrace. We are not supposed to drink coffee inside if we are not seated, and you won't be seated. These are the rules. I'm not making the rules. Secondly, please try to keep your mask at all time unless you're giving a talk. And please keep your mask on the posters. All right. And except for these, well, it's a pleasure to be here. We are really proud of organizing this mirror event. I think it has been like 2 years that we didn't have a real event like this, and many people, I certainly do, start to feel Zoom fatigue, and presenting your poster in front of silent audience is maybe not ideal. So hopefully today you will have the occasion to present your poster in front of real people. So enjoy it. We thank the CIS in EPFL who really helped us in the organization of this conference. So thank you, Etienne. Thank you, Lenka and Nicolas. Maybe you can wave at the audience. And Jan. So, please enjoy the conference. I think that will be something that will happen more. I mean, the world is changing. Maybe it's a bit stupid to travel 20,000 kilometers just to give one poster and come back to your home. So I think we are going to see more and more events like this one. I think we are really particularly proud that we organized this one, and then we saw similar events pop up everywhere in Europe. Our friends in Paris are also doing an EPFL, a Paris Mirror NeurIPS event. That will be on Wednesday. Our friends in ETH are doing one tomorrow, I think, and there is a similar event in Tübingen. So welcome to the future. I think today is a special day for us. All right, that's all I will have to say. A reminder of the program. We have the spotlight talk this morning. Then we all gather in front of the posters. There are many places where you can find food around. If you are from EPFL, you don't need me to know this. If you're not, well, just look around up there or Google. It won't be so hard. At 2, we reconvene and we have the oral talks. And then we can finish with the posters. We will have some picture taken by our photograph. Hello. If you really don't want to be taken into picture, you can just say it. Otherwise, we will assume that you have no problem with your copyright images. All right, without further ado, we'll let the floor to Lenka Zdeborova that will chair this morning session. Thank you, everyone.
Thank you, everyone. I was picked to chair this session as I was doomed as the one that will actually be able to make the people stick to the 5 minutes. So sorry if I chase you away from here. So we have the slides on, and the first talk, we put them in the order in which they are on the webpage, except the 2 that ask us to be at the end. So Etienne Boursier will present the Decentralized Learning in Online Queuing System paper that got a spotlight at NeurIPS. So here is his real spotlight.
So thank you for the organization and the introduction. So I have the honor to speak as the first of this spotlight session. So I'm going to present shortly the paper on decentralized learning in online queuing systems, which is a joint work with Fleur Saint-Nac and Diane Percher back in Paris. So I'm going to first present the model shortly, which is motivated by packet routing through servers. So assume you have a single queue. In that case, the goal for this queue is to get rid of the number of packets it accumulates each time. So each time some packet arrives with some probability into the queue, and just to choose a server where to send this packet, and its goal is to clear all its packets. So in that case, you can just see the problem as a multi-arm bandits, as a classical stochastic multi-arm bandits. But it becomes much, and so if the packet is not transmitted, it goes back to the queue. But it becomes much harder when you have several queues, because in that case, if several queues send to the server can treat a single packet at a time. And so you have some collision between the queues when they choose the same servers, and their goal is also to coordinate to avoid choosing the same server at the same time. And so in the end, the goal is to design algorithms or strategies that are stable in the sense that the number of packets does not explode with the time. And so here is the state of the art for this problem. So for the centralized case, we know that for eta, which is the main parameter of the problem, so eta is the ratio between the arrival rates and the server rates. And we know that for eta larger than 1, we have stable centralized strategies. And we already knew some results. So for eta larger than 2, that all no-regret policies are stable. And that for eta larger than e over e minus 1, all the Nash equilibria of the game are stable. And so what we show in this paper is that we provide a stable decentralized strategy for any eta larger than 1. So we kind of reach performances comparable to the centralized case in the decentralized case. So just to summarize quickly the contributions, we show that patience is not enough actually for stable learning in this problem. And we need to also enforce cooperation between the queues. And we propose the first decentralized stable learning strategy for this problem. And so if you want to know more about this, you can join me at the poster session. So I am poster number 2. Thank you.
Thank you, Etienne. As he said, the questions will be at the poster session. The second spotlight is by Bruno Loureiro, presenting the paper Learning Gaussian Mixtures with Generalized Linear Models, Precise Asymptotics in High Dimensions. Oh, I think I know that one.
Okay, so should I time it, or is there going to be a timer there?
No, go on.
Okay, so this is joint work with Gabriele Sicuro in London, Cédric Gerbelot in Paris, Alessandro Paco, who was a master's student here at our group, and our hosts today, Lenka and Florent, here at EPFL. So this work is about classifying Gaussian mixtures. So we are going to be considering generic Gaussian mixture data. So we have K clusters, and condition on their labels Y. They are Gaussianly distributed with generic covariance and generic mean. So given this data set coming from this Gaussian mixture, we want to classify it by doing empirical risk minimization. So that's just the usual thing you do in machine learning. And in particular, we're going to be considering the case where we're trying to classify them with a generalized linear model. So we are going to be minimizing a convex loss L, and we have some penalty R with some strength lambda. And so here, for example, we can think about square loss, like just least squares. We can be considering cross entropy minimization. And the goal here is, given this Gaussian mixture data, and given the loss and the penalty that you want to minimize, characterize the error asymptotically. So we're going to be in particular interested both in generalization and training error. So generalization, we're going to focus on the misclassification errors, which is the probability of doing a mistake given a new data point. And for the training, we can either consider the misclassification training error or also the training loss. And the goal is in particular to characterize this problem when it's hard. So when the clusters overlap a lot, and when you are in high dimensions and it's hard to classify. So our main theoretical result in this paper is going to be a characterization of the error in the asymptotic limit, where the number of samples coming from this Gaussian mixture and the number of dimensions go to infinity at the same rate. So the result, we prove rigorously that actually the error, which is a high dimensional quantity, going to concentrate into some quantity which only depends on k by k matrices. So k is the number of clusters, remember. So here we are changing a high dimensional hard minimization problem for a low dimensional easier minimization problem that you can solve in your computer. So we can characterize the error exactly in this limit. And I'm not going to show you the expression for the error because it's very messy, and the goal is just like to give a taster. So given this characterization, what can we do with that? So we can study many things that statisticians are interested. So for instance, we can characterize when data is separable or not. So for example, characterize the set of interpolators of the given laws that you're interested. So let's say you're interested in cross entropy. We know that when the regularization goes to 0, this converts to the max margin. So you can characterize, for example, when your data can be perfectly separated by the margin. So here is an example as a function of number of clusters. The more clusters you have, the harder it gets. Depending on the covariance as well, it can be harder or easier, depending on the balance of the clusters. These are all things that you can characterize using our formula. So something else that you can study is like how this changes with regularization, and how, as we regularize more, you can achieve better and better performance, and you can find the optimal regularization that gives you performances close to the base optimal error in the case where, for instance, your clusters are balanced. So that's something else that you can characterize with our formula. You can also study different kinds of regularization. So here is an example where we take just 2 clusters and we compare doing a lasso in a model where the means of the clusters are sparse. So you can see, like, you can characterize different regimes where lasso does the same or better than just standard L2 penalty. And finally, we also played a little bit with real data. So here we observe in some of our previous papers that actually these errors, when they concentrate in high dimension, they are only sensitive to second order statistics. So here we probed whether this is going to be the case also for Gaussian mixture classification. We got some real data. We trained a neural network to learn some features of this real data. And then we plugged the covariances that were estimated empirically from the real data into our formula, and we see whether the performance achieved by the theory, which is in solid lines, match the experiments with this real data. And actually you can see a very good match, meaning that actually the Gaussian model is characterizing also something about the realistic data. Okay, so that's all I have to tell you. And if you are interested, come to our poster, we can discuss more about it.
Thank you, Bruno. And the third spotlight paper that we have here is Uniform Sampling over Episode Difficulty by Seb Arnold.
So hi everyone, my name is Seb, and today I'm going to present Uniform Sampling over Episode Difficulty, which is joint work with Gunit Dhillon, Avinash Harichandran, and Stefano Soato. So our work focuses on episodic training in the few-shot learning regime, and as a brief reminder, in few-shot learning, the goal is to learn a model that is able to solve a new task, given limited amounts of labeled data. One way to do this is via episodic training, which proceeds in 3 steps. First, we're going to sample an episode. You can think of a task. Then we're going to solve this episode, and finally update our model so as to improve our performance on the next episode we're asked to solve. Our work focuses on the first part of those 3 steps, and namely we ask the question, how should we sample an episode so as to improve downstream transfer accuracy? Our contributions are threefold. First, we present a thorough analysis, empirical analysis of episode difficulty. Second, we propose a simple method to approximate a large number of sampling distributions over episodes. And finally, our main results. We report that uniform sampling over episode difficulty outperforms alternatives. So how do we typically sample episodes? We start with a base data set and choose n classes from it. Then for over those n classes, we're going to sample a small support set used to solve the episode, and then a small query set used to evaluate how well we've solved that episode. Now, solving the episode can be done in many ways, but the simplest way is to embed all of the samples from the support and the query set into a learned embedding space and just do near-centroid classification in that space. So in the first part of our empirical analysis, we show that episode difficulty is approximately normally distributed, as can be seen on the right-hand side of the slide. Here, the definition of episode difficulty is simply the negative log likelihood of the query set for a model that has been adapted using the support set. Why this definition? There's mostly 2 advantages. First, it's easy to compute and readily available during training. And second, it applies to all methods, whether they are from the metric-based family or gradient-based family like MAML. In the second part of our analysis, we show that Episode difficulty is mostly invariant to a few modeling choices, including the network architecture, the model parameters during training, and the choice of training algorithm. And that's important because it motivates our use of important sampling for approximating other episode sampling distributions. And in fact, in the second part of the paper, we compare 5 distributions against each other. The first one is the baseline that we've already discussed. Then we have easy and hard mining, where we exclusively sample from the 50% harder or easier episodes. Then we have curriculum learning, where we, at the beginning of training, we start by emphasizing easy episodes, and at the end, we emphasize harder episodes. And finally, we have uniform sampling, where we sample uniformly over the entire range of episode difficulty. So in our first benchmark experiments, we pitched those 5 methods against one another on 24 different scenarios where we have varied the network architecture, the training algorithms, the data sets, and the few-shot settings. And we see that if we tally how often a method, a sampling method, is among the best performers, uniform dominates and baseline is a distant second. So then we can zero in on baseline versus uniform. And this is done for the cross-domain transfer tasks. So what we do is we take pre-trained models with either baseline or uniform, and we evaluate them on unseen data sets. What we see is that, again, uniform dominates. And as our final experiment, we can take a state-of-the-art method like FEAT for few-shot learning, replace baseline sampling with uniform, and again, we see improvement across the board. So with that, I'll thank you, and I'll thank my collaborators, Gunita, Vinash, and Stefano. You can find more information on our website, or come talk to me at the poster session, of course. Thanks.
Cool, thank you. And the next paper is Sequential Algorithms for Testing Closeness of Distributions, presented by Aadil, Oufkir.
Hi everyone, I'm happy to have this opportunity to present this article at this event. So this is a joint work with my advisors, Omar, Nicolas, and Aurélien, and it is about testing closeness of distributions using sequential algorithms. So in these few minutes, I would like to present clearly the problem of testing closeness, along with the differences between sequential and non-sequential settings. So testing closeness problem is about testing 2 distributions, D1 and D2, unknown, on the set of integers between 1 and n. So the tester doesn't know D1 and D2, but can ask for samples xi iid from D1 and yi iid from D2. And he would like to distinguish between 2 hypotheses. The first hypothesis, H1, is simply D1 equals D2, while the second hypothesis is distance between D1 and D2 greater than epsilon, where epsilon is a positive constant. So the tester is a probabilistic algorithm, so he has some error, and we would like to have an error at most delta. So for this specific problem, if D1 equals D2, we would like to have a tester that accepts with a probability at least 1 minus delta, while if D1 is epsilon far from D2, the tester should reject with a probability at least 1 minus delta. Note that here the m, the length of samples, xi and yi, is fixed before even starting the test. And this problem is fully solved by Diacono-Nicolas and others, and we have the optimal sample complexity, which is sublinear. So if n is very big, it scales as n to third, and it is optimal in all parameters n, delta, and epsilon. So if we would like to improve, we should change the setting. And one thing we can do is changing the m and allowing the tester to have the possibility to choose the stopping time according to the previous observations. And this is called sequential setting. So if xi are the samples from D1 and yi are the samples from D2, a sequential algorithm is given by a stopping rule T that has as input 2 words of length k at step k and returns either star, equal, or not equal. Equal referring to accepting H1, not equal referring to accepting H2, and star means that the tester would like to have more samples. A new sample from D1 and a new sample from D2. So in order to compare sequential and non-sequential algorithms, we define two stopping times, tau1 and tau2. Tau1 is the first time the stopping rule returns equal or accepts H1, and tau2 is the first stopping time the stopping rule accepts H2. And similarly, we ask the algorithm to be delta correct. That is, if D1 equals D2, we would like to have the stopping time returning equal before not equal, with a probability at least 1 minus delta. And if D1 is epsilon far from D2, we would like to have a stopping rule that returns not equal before equal, with a probability at least 1 minus delta. So the main question of the article is, can sequential algorithms outperform non-sequential ones for testing closeness problem? And we gave different answers, positive ones and negative results for this question. In particular, for small alphabets, we give the optimal sample complexity for sequential and non-sequential settings to the constant. So if you have any questions, we can discuss this at the poster session. Thank you.
Thank you, Aadil. And the next spotlight paper we have at this mirror event is on the power of differentiable learning versus PAC and SQ learning by Emmanuel. Abbe.
Thank you, Lenka. Okay, so yes, it's the first one. I mainly like the second one, so I will talk a bit about the second one too. Please send me signals when the time is over, when we are close. So deep learning combines effectively overparameterization and gradient-based training. What we are interested in understanding is how sufficient is the framework, meaning is it specific to certain data distribution like images, and do we need an alignment with the architecture so that you can catch the signal? Is it universal? Is it the entire PAC class? Is it limited to statistical query learning, etc.? We also want to know how necessary is the framework, meaning do we need really overparameterization, or could we do everything with kernel, etc.? Okay, so this is a key quantity. It seems like those questions, to answer them, we need to understand what type of neural networks we allow. It seems very important that we put the right framework to which neural networks can be used or not used. And this spectrum is kind of the entire complexity layout. On the very left, you have the simplest model, fully connected 2 layers neural networks. On the very right, you have something where you don't have any conditions. You just need the neural net to be polynomial size. Okay, in the middle, you have what is probably used in practice. So this is the two I call regular networks, what's very structured, and free networks, everything you want. So the first paper is about the extreme right. What happens if you don't put any conditions on the neural networks you can use besides the fact that they have to have a polynomial size? And this is the results in one picture. What we can prove is that if you use SGD on neural networks, then you can, of free neural networks, then you can actually learn anything that is in PAC. So it's universal. So this solves the problem that was posed in the book of Chalet-Schwartz. It's not only optimization and estimation errors that you can control, but you can also control the estimation error with SGD. So we know this is not the same if you do statistical query learning, and counterexample are dense parities. And in fact, what we show is that when you use full GD on the population, surprisingly, you get less than SGD. You get that you saturate that statistical query learning. So I don't have time to define SQL, but that's the picture. So SGD is slightly more powerful than is GD. And then in between, you have a phase transition when you use a batch size. So this is the main result of the paper that is the spotlight, is that if you use a batch size with B samples, fresh samples, but per time steps, if you have a precision for the gradient, which is tau, the number of bits you use to store, then there's a phase transition. We cannot prove exactly the phase transition. We prove a slightly weaker version. we prove this thing here. So what I believe is true is that if b tau is small, then you get PAC for batch size SGD, and if b tau is large, then you get SQL, and we get a factor a power 2 here that's probably suboptimal. And then the last part is that we know also that this is strictly better than kernels. So the picture looks like that. SGD gets everything, GD saturates at SQL, you get the phase transition in between depending on the batch size, and all of these are better than what you can do with kernels. And the counterexample for kernels, I won't discuss it. Okay, so this is the formal definition of these sets. I don't think in 5 minutes we should go through them. So I'm assuming that you have an idea of what PAC is, etc. So now I'll tell you in the last minute a little bit about the right side, which is the second paper. Sorry, the left side. So when you do the exact opposite, instead of having free networks, now it's going to be very structured networks with IID weights and fully connected or Herder-Schwenny connections. And this is the picture we believe is the right one. So what I call GD-NN reg is when you use a regular initialization of this kind. And this is strictly less than what we had before. And what are the functions you can learn? It's functions that are of this kind. So, I define everything in a bit of a cartoon version because of the time, but all these things are defined properly depending on the Fourier coefficients of the functions. But that's a function you can learn when you use a regular initialization. You need the high degree coefficients to be learnable from the lower ones. So here, for example, x1, x2 is degree 2, but once you have x1, it's degree 1. It's just composing x1 with a free variable. x1, x2, x3 is degree 3, but once you have x1, x2, it's just a composition of degree 1 again. So this is what a staircase here. You can actually get high degree coefficients. If you only had this term, if you didn't have all of this, then this you cannot learn, and that's the red region. So this is the high degree functions. You cannot learn this with a regular network. But if you climb it and you also have the coefficients that are in staircase, then you can learn this. So this is what we believe you can learn with regular networks. It's still better than kernels and growing staircases of this kind where P grows is a counterexample. That what you cannot learn with kernels. And it's not as much as SQL because you can have a staircase where you truncate the first term here, but you go all the way up to the last term here. And this is SQL learnable, but not learnable by deep learning on a regular net. So that's essentially the picture we have at the moment.
Okay, let's see more at the posters. Thank you, Emmanuel. And next spotlight, sixth one, is the credit assignment in neural networks through deep feedback control by either Alexander or Matilde, or both of them. Alexander, okay.
All right. Hi, everyone. I'm excited to share our recent work on deep feedback control, which I did together with Matilde, as said. So our work centers around the hierarchical credit assignment problem in the brain, which asks the question of how do you need to change a synapse in order to improve the global behavior of the animal. And especially when the inputs are processed in some hierarchical fashion, like for example in the visual stream of the cortex. Now we can investigate this question by using simple artificial feed-forward neural networks, and there it's usually solved by using the backpropagation algorithm. However, we cannot directly use this algorithm as a hypothesis of how learning is happening in the brain because it has some biological issues. And the main one is a weight transport issue, because in backpropagation you need to have exactly the same synaptic connection in the feedback path as in the feed-forward path. However, these are two separate pathways in the brain. So this motivates our central question of our research, which is, can we do principled credit assignment without this need for a strict alignment between the feed-forward and feedback path? And so we address this by introducing a new method, which we call deep feedback control. And now, instead of using feedback directly for updating the synaptic connections, we're going to use feedback first to change the neural activity of your network, and then we will use these changed neural activations to update the synaptic connections of the network. And we're not going to change the neural activations in a random fashion. No, we're going to use a feedback controller at the output, which will push your network towards a desired output target, which, for example, you can think of as the label of your data sample. And so then the intuition is that at the beginning of training, you will need to have a lot of help from your feedback controller to reach the label, whereas at the end of training, you will need almost no help at all. And so to let the controller influence the neural dynamics, we need to introduce some neural dynamics, which we do by simple leaky dynamical equations. And so at steady state, these equations just collapse to a normal feed-forward neural network. However, importantly, now we can add the influence of the controller by just simply multiplying your feedback control signal by your feedback weights Q. And then the next step that we need to do, of course, is to use these changed neural activations to update your synaptic weights W. And for this, we're going to use a multi-compartment model of a neuron, heavily inspired by the cortical pyramidal neuron. And so in here, we have 3 compartments. At the bottom, we have the feed-forward compartment, integrating the feed-forward input of the neuron. Then at the top, a feedback compartment, and in the middle, the center compartment, which combines the two. And then we can use a very simple plasticity update rule, which just takes the difference of the central compartment and the feed-forward compartment as some type of an error signal, and then it multiplies this as usual with your presynaptic activity. All right, and the next thing that we want to show is that this new method that we introduced does some principled mathematical optimization. And so we link it to Gauss-Newton optimization with a mini-batch size of 1 if 2 conditions are satisfied. And the first one is just a flexible alignment condition on your feedback weights, and the second one is some stability condition. And then, importantly, these 2 conditions are actually quite flexible. So what we do is, in a toy experiment, we generate a lot of random feedback matrices Q, which satisfy these 2 conditions. And so these would be the blue dots over there. And then if you compare it to backpropagation or its approximations, which need like a very strict alignment between feed-forward and feedback path, which would be the red cross over there, you see that our new method, DFC, actually allows for much wider feedback configurations that all lead to optimal credit assignment. All right, so in conclusion, we introduced deep feedback control, which uses a feedback controller to push the network to a desired configuration, and then it can use this change neural activity to update the synaptic connections. And we can make this fully local in both time and space if we use the multi-compartment neuron. And then furthermore, we show that we actually can do principal credit assignment without this strict need for alignment between your feed-forward and your feedback path. And not shown in here, but it's also competitive performance to backpropagation on some very modest computer vision tasks. So with this said, the only thing left for me is to thank all these amazing people here on the slide, of which Javier is actually sitting there. And then, of course, also you for your interest in our work. Thank you very much.
Cool. Thank you. And next one, 3 left. Precise characterization of the prior predictive distribution of deep neural networks by Lorenzo or Gregor?
Yeah,
Lorenzo, okay. Thanks.
Thanks. So in this talk, we deal with fully connected neural networks. The L is the depth, and we have Gaussian parameters with fixed variance sigma square. And we try to understand at initialization, as the input propagates through the network, what is the distribution of the intermediate layers units. And this is the notation that we will be using. And P is the density here. The main tool that we will be using is the Meyer-G function, which is defined as this complex integral, where inside we have this product of gamma functions. And we have exactly L parameters, B1 to BL, that appear inside the product of gamma function. And this will be fundamental. Yeah, let's start with a linear network. We can characterize the distribution of a linear network at initialization. This is well known in the literature. And the density is just proportional to a Meyer-G function, where I have exactly L coefficients, and the coefficients depend only on the width of the network, as you can see down here. Now let's go to the more interesting case of a ReLU net. And here the intuition is that as the input propagates through the network, here, I have some units that will be active and some units will be inactive due to the effect of the ReLU activation. And we define two subnetworks with the same number of active neurons per layer induce the exact same density. And we call these subnetworks equivalent when they induce the same density. And now the density of a ReLU network can be characterized as a linear combination of all equivalent linear subnetwork that you can have from your original network. Plus, we have another term that is just the special case in which all the units of one layer are inactive, and then essentially the input cannot propagate anymore through the network. Now, once you compute the density, then you can derive the moments of the distribution at the initialization. And here we have a particular choice of the weights. It's called NTK parameterization. And we have M, which is the width. And yeah, we can compute the moments in closed form at any width and depth. And now from this complicated equation, we want to derive some limiting behavior as the width and the depth go to infinity. So this is the picture here. We have simultaneous limit of width and depth. And we do so by parameterizing the depth as a function of the width with this gamma parameter that is fixed. And if you do so, you can simplify that complicated expression for the moments. And actually, we have an interesting limiting distribution that is the moments converge to the moments of a log normal times the moments of a standard Gaussian. So this is the effect of the depth is essentially in this log normal part, and the effect of the infinite width is in this Gaussian part, essentially. We try to see how this log normal regime approximates finite width and depth network visually. So here I plot the PDF and the CDF of the distribution as the depth increases, and I fix the width. And essentially, you can see that as the depth increases, I depart from the Gaussian regime. The Gaussian is the orange one. So as I increase the depth, I depart from this Gaussian regime, but the log normal surprisingly approximate the distribution of the network quite well. Now, in the final slide, we look a bit at the tails, because as you can see, the tails become more and more heavy as I increase the depth. And in particular, we look at the kurtosis, which is a standard measure of heavy tailness of the distribution. And you can see that essentially the tails become more and more heavy-tailed with depth. This is the precise expression. Yeah, so the conclusion is that we derive a closed form expression for the PDF and moments of a ReLU net, and we identified this new log normal regime at infinite width and depth. And we had a closer look at the tails, showing that they become more and more heavy-tailed with depth. Yeah, this is the end of my talk. See you at the poster session. Thanks.
Thank you. Thank you. And we are going on with the paper Prototypical Cross-Attention Networks for Multiple Object Tracking and Segmentation by Leike.
I'm going to introduce our work, Prototypical Cross-Attention Network for Multiple Object Tracking and Segmentation. This is a work done by the Computer Vision Lab of ETH Zurich and HKST. So our problem setup is we want to detecting, segmenting, and tracking all the interested video objects in the video. And then the key motivation of our work is that the video contains the multiple views of a single object. So this temporal information can be used to improve for example, the segmentation mask quality. So we want to improve the temporal efficiency. So the previous method, you could see, they generally get the result from the individual frames, and then only do the association by the detection result. The temporal modeling is only limited to single frame or just between two adjacent frames. So in our network, we call PCAN. In our network, we design a method that to condense the high-resolution frame embeddings into the prototypes by Gaussian mixtures, and then use the cross-attention to exploit the memory prototypes to utilize this kind of temporal information.
and finally to help the final frame prediction result. So the benefit is that it produces efficiency because the high resolution frames are condensed to the prototypes, and also is achieve a good result. So it's mainly two perspectives. First, we do the frame level by reconstruct the past frames to align with the current frame, and then we specifically do the instance level to utilize the instance-specific feature for each video object. So let's first start with the frame level module. So given the past frame in the memory bank, we first condense get its key and value embeddings. And then we use the EM operations to get its key prototypes and value prototypes. Then given the current frame feature, we get its query key embeddings. And then we use the cross attention to fetch the memory prototypes and do the linear feature fusion with the current frame. And then goes to this is the frame level cross attention. And for the instance level, because we have the initially detected object mask, so we use it to identify each video object. And then we separately model the foreground and background features of each video object. And then these prototypes, for example, the positive prototypes of the foreground will be propagated and updated by our designed recurrent scheme. And this is instance level. And you can also see the instance attention map by the foreground and the background. They will focus on the specific region. And these attention maps will also be used to help our final segmentation result. So these are some visualizations of the frame level prototypes. You could see that it will correspond to some semantic concepts, such as the human body and like the skateboard and the tennis racket. And this is the instance level prototypes. You could observe the temporal consistency. Like we sample the first prototype, it will consistently concentrate on the front part of this car. And this temporal consistency is learned implicitly. And here are some quantitative results that we achieve a large performance gain on the two largest MOTS benchmarks. And this is the ablation that to say, how about we change the temporal length, the memory tube length, and how about we change the instance prototype numbers. So how many prototypes we want to condense each video object in. And here I just show one video result because of the time. So some of our MOTS tracking result on the BDD 100K dataset. So it has a direct and important application in the self-driving scenario. So I think the main reason why we can get the spotlight is that we design a method that can utilize the temporal information with efficiency and online speed. So that's the main reason and our good performance. Thanks for watching.
Cool, thank you. And the last of the spotlights we have here today is Repulsive Deep Ensembles are Bayesian by Vincent Fortuin.
Cool, thanks. Yeah, this is joint work with Francesco, who can't be here today, unfortunately, but he's looking for PhD positions currently, so if you have any hints, let me know. And in this work, we're dealing with deep ensembles, which are this very popular method recently where you just train an ensemble of neural networks. And the way you do it typically is just you have different neural networks that you initialize randomly, and then you train them independently with just gradient descent. So in this case, on a log posterior. And that's computationally very efficient, so people have been doing that a lot. But what's recently been discussed is whether that will actually approximate the Bayesian posterior. So there's been people that say we can kind of treat it as approximate Bayesian inference. But the problem is that it doesn't offer any guarantees due to the problem of the lack of diversity in these ensembles. So the diversity that you have in the ensemble is basically just due to the randomness of initialization, the noisy gradients, and the number of different local optima. So what happens if you have a posterior like this is that if you have any number of ensemble members in the normal deep ensemble, they will just always converge to the same modes of the posterior, while what we ideally want is to characterize actually also the shape of the modes, right? And so our idea was to introduce a repulsive term so that these little ensemble members here can actually push each other away from each other so that they kind of spread out in these modes instead of all falling into the mode. And then the question is, how do we actually parameterize this repulsion? So we basically had the idea to take this, what we call the driving force, which is just the normal gradient that you have in the deep ensemble, and add a repulsive force that is basically a weighted sum over kernel gradients. So the kernel measures how similar two ensemble members are, and then the gradient of the kernel will push them away from each other. So now the question is, how do you choose this weighting parameter, right? And it turns out that if you choose it in the right way, then this repulsive ensemble actually converges to the base posterior. And so to see that, you can write the measure, the empirical measure of the ensemble as this sum of Dirac measures, and then write down the KL divergence functional, which we can then write down the gradient as a Wasserstein gradient descent. And then the problem is that the gradient of the log empirical measure is unfortunately not tractable because of this Dirac. But we can approximate it using kernel density estimation, right? And so we get this term here, which then basically, if you put it back into the equation of the Wasserstein gradient flow, you see that this is basically our repulsive equation from the last slide, with the beta parameter chosen to be this thing. So if you choose beta to be this, then you get a repulsive ensemble that actually converges to the base posterior. Now, there's still one problem here, namely that the weights could possibly implement the same function due to all the weight space symmetries in neural networks. So we might get a nicely repulsed different weight particles that still have the same function in function space. So we then also try to move the repulsion into function space by considering a canonical projection. So that's just basically estimating the function at different points. And then we can write down this whole update equation from the previous slide in terms of the function, so the log posterior of the function, and also the kernel of the function in terms of this canonical projection. And then we just take this whole functional gradient and project it back into weight space using the Jacobian of that particle. And so then we see that our repulsive method in function space gives us these nice uncertainties. So in terms of here, in between uncertainties, we see that the true posterior, or at least the Hamiltonian Monte Carlo, which is our gold standard, has this uncertainty, but standard deep ensembles and also the white space methods don't. But if we have the function space repulsion, then we get this uncertainty, and the same we see in 2D classification, where we also get these very nice uncertainties that you have in the HMC, but not in the weight space methods. So on MNIST, we can also see that we get better OOD detection in terms of OROC. We also get better likelihoods and somewhat decent calibration. So in summary, we showed that we can introduce this repulsion in deep ensembles to converge to the true base posterior, and if we do it in function space, we actually get nice convergence to nice uncertainties. And there's a few open questions that I'm happy to talk about at our poster. Thank you.
Thank you very much. So that was pretty awesome appetizer to more that is happening in the posters, not only on these papers, but about 50 other papers that are presented there. So without further ado, let's go to see them. Thank you, everybody.